So I would like to welcome our keynote speaker, Russel Schwartz. He came all the way from the US for us. So Dr. Russel, welcome.
Well, thank you. I'm just going to set up my talk on Zoom here. Can everyone hear me through the microphone here?
You can disable the video, we enable it here.
Okay. Hey, thank you, everyone. It's really an honor to be invited to present at this meeting. I'm really happy to be able to talk to you about some of the work I've been involved in bioinformatics curriculum development, and talk about some of my perspective on where we've come as a field and where we're going based on the aspects of this that I've been privileged to work on. So I've had a number of different roles that I think have bearing on bioinformatics curriculum development and give me a perspective from which I believe I can talk about some of the topics that hopefully are of mutual interest to us. I like to think that my start as a bioinformatics educator actually began more than 20 years ago, almost 30 at this point, as a student of computational biology. When I was really trying to figure out for myself at an institution that didn't have any computational biology degree programs, they were quite rare back then, what it was I needed to know to be able to do my job as someone who wanted to get into the field and was starting to work as a researcher, but didn't have any formal training. I was doing degrees in computer science, but basically trying to build my own program. And I learned a few lessons, I think, then, and probably the most important one that's guided a lot of my thinking since then is that computational biology is not just a fusion of traditional fields. It's not just taking biology and computer science and sticking them together. It's its own discipline that has its own unique knowledge beyond what you can gather from pre-existing disciplines. And because of this, it needs to develop its own teaching materials suited to what we need to know to be able to do our job. And that was the beginning of being able to work on this in a number of different roles. First as a course instructor, once I got my own independent faculty position, creating a number of classes to try to teach computational biology to different cohorts, as a curriculum developer who helped design or redesign a number of programs in the area, eventually a program administrator running some of these programs, and in my latest role as a department head running a computational biology department that offers a number of degree programs where I'm in more of a supporting and facilitating role of the people who are doing most of the day-to-day work of running all of these programs from the pre-college to the bachelor's, multiple master's and PhD levels. Throughout much of this, I've been working with the international bioinformatics education community, which I got into through the International Society for Computational Biology, ISCB, where I've been a member of the education committee for some time, and I'm currently one of the co-chairs of the community of special interest in education, COSI. And what I wanted to do in this talk is give some of my perspective from having worn these different hats throughout my career of what I've learned working on bioinformatics locally and how I've worked with the international community to try to turn that into lessons that we can share with one another, to try to learn from the community and share what I think we've learned. So this talk is going to jump a bit back and forth between things I've worked on my local institution and things I've been working on as part of this community of educators. And in many ways, I think that is really my philosophy of how to be a successful educator, that we really need to go back to our local institutions, work on the small scale and try out ideas and see what works in our own cohorts, and then go back to the larger community to share what we've learned and learn from others about how to overcome our challenges. So starting with the story at my own institution, we offer a number of different degree programs, including bachelor's, master's, actually a couple of masters now, PhDs. I want to very briefly mention these, but mostly focus on a different aspect of the work, which is developing courses to train a cohort who is outside my department, so experimental biology cohorts, and what we can do with respect to curriculum development when it's not our curriculum that we control. Just to briefly talk about the degree programs offered in computational biology, specifically by my department, we do offer a 4-year bachelor's degree, which in some ways is where we can be most aspirational about what we're trying to do. We have students for 4 years, they take a lot of classes, we can control which classes they take, and so we can really be very ambitious about what it is we really think someone entering the field should know and make sure they get that training. At the opposite end of the spectrum would be our master's programs, where we have students who can have very heterogeneous training coming into the program. We want to get them to a common level of training going out of the program. We don't have them for that long, so 2 years, sometimes less than 2 years, because they're motivated to get out quickly, and basically can spend a year giving them foundational courses to get them up to a common level, and then really in the second year, get them to the actual computational biology and try to get them to a fairly advanced level by the time they graduate. And then at the PhD level, we typically have our students for about 5 years. It's variable depending on the student. Here we can take students where we have a lot of control over what they've taken coming in, although it's still quite a heterogeneous cohort, but at least insist on a high level of training, even if it's from different directions. That lets us be pretty ambitious in developing a core curriculum that we would want to say is what we think everyone with a PhD in computational biology should know. And then from there, allow the students to feed into various lists of advanced electives to really get to advanced graduate work in their area, alongside professional development, and of course, largely research mentorship through their thesis proposals. So as I say, that's not what I want to focus on here. I thought I could give this talk entirely on that aspect of the work, but I want to talk about the courses that we've developed and lessons for training experimental biologists, because in some sense, I think the computational biologists are actually the easier problem. We have a lot more control over what we do there, a lot more ability to make things work how we think they should be working, which doesn't make it an easy problem by any means, but it's a little easier than the experimental biologists, where we have a lot less of their time and a lot less ability to control what's going on in the rest of their time. So I wanted to talk about a couple of experiences there and how these feed into some of the activities I've been involved with in the international community. And I wanted to start with a story that begins almost 20 years ago when I was a relatively new professor, working on trying to get our undergraduate biology students trained in computational biology. At the time I came into this was kind of a summary of what our curriculum looked like. And it was a fairly traditional biology curriculum. We did actually have a computational biology class, although it was an elective class. This was developed by another faculty member at my institution, Robert Murphy. And it was really a class designed for specialist computational biology students. A very small number of biology students would take it as an elective, but really wasn't designed for the average biologist. It was something that they would usually take relatively late in their studies, and they would usually take it without having had any programming, any computational or statistical mathematics. We were unusual in that even 20 years ago, all our biologists were required to take a computer programming class, but it was actually not very effective for them because very few of them wanted to take it. They didn't understand why it was useful to them. They put it off as long as possible. So usually it would be one of the last things they take before graduating. And we had no requirement for statistics, no requirement for other kinds of important math that would feed into computer science. So it was quite a challenge to develop a class, but we set out to do what we could to teach what we thought an experimental biologist should know. I put down here our official learning objectives. And I'm not going to bother reading these. Anyone, I imagine, can see this later if you really want to know the details. But what I'd like to say is that we really only had one unofficial learning objective, and that is that we wanted our students to learn what they needed to know about computational biology to be the best experimental biologists they could be. And this was really a very different focus than the class that had existed before. And what that came down to from our perspective is that there were certain things our students needed to know about computational tools. And I use tools here very broadly to mean not just actual pieces of software, but in some cases algorithms, in some cases data sources, and perhaps most important, ways of thinking about a problem. Because the ways a computational person, or what we would now call a data scientist, thinks about a problem is quite different from how a typical experimental biologist was trained to think about a problem as of that time. And we really felt that these ways of thinking were important to being more effective biologists. They needed to know what kinds of problems that they could solve with those tools. And they needed to know some things about computer science as well as foundational areas like statistics to use these effectively, to be able to do things like think about abstracting a problem, choosing appropriate methods, interpreting data outputs, and so forth. One of the things that was surprising, I think even to many of my colleagues at Carnegie Mellon in trying to develop these courses, and even to me at first, is that we realized we had to teach our students quite a lot of biology and biotechnology to teach them computational biology. Because even just in what we would call experimental biology, what a biology student was learning then was not necessarily what they needed to know about biology to be able to appreciate bioinformatics. For example, they would learn nothing about sequencing in a standard biology curriculum then. We had to teach them sequencing. We had to teach them why that was important and what things you could solve from it. So all of that fed into trying to design a new class for computational biology for biology students, just showing the curriculum here broken into a series of weekly modules. There were two basic halves of this: genomics and molecular biology, which I was teaching, and modeling and image informatics, which my co-instructor was teaching. And in a typical week of this class, we would try to cover some fundamental ideas. These might be fundamentals of biology, they might be fundamentals of math or computing. In this case, a typical week, we might have basics of statistical hypothesis testing, might be one lecture. And then we'd bring that into a more concrete level, for example, talking about how that's relevant to sequence alignment, and then really bring it down to the practice of something a biologist could do in the computer lab, working with specific tools, in this case, the BLAST family of tools, and then actually bring the students into a computer lab for a recitation section where they would solve toy research problems using these tools, and that would be reinforced with homework assignments where they would go off and do more involved kinds of assignments with similar concepts and tools. So that was part of what went into creating this course. But one of the things we realized relatively quickly is that we could create a course that we thought was good for this population, but that didn't mean it was actually going to meet its needs. Even when we created this, we were pretty much getting a fairly small cohort of the biology students taking it. And we realized that we had to do a lot of work beyond just this one class in order to make this something that would be useful to the entire biology student body. We had to make room for it in the curriculum. We had to ensure that the curriculum could be adapted so that students got the necessary prerequisites so that we could teach this at a reasonable level. And we had to ensure that there were opportunities for the students to get reinforcement outside our class. So we really couldn't think of this as just one class in isolation. It was a problem of an entire curriculum, in this case, a biology rather than a computational biology curriculum. And so we had to do a number of years of work with our experimental biology colleagues to really make this a workable solution. And we had to dig into the curriculum in a number of different ways. So we had to look at the general math and science requirements that were being given to our biology students. And the reason for this has to do with something that pretty much everyone who's tried to teach computational biology to biology students runs into, and that is that you can't add something to a curriculum unless you take something else out. And as soon as you try to take anything out, no matter what you identify, someone will champion it and say, that is absolutely necessary for a biologist to know. It can't come out of the curriculum. So this was a multi-year effort to try to find something we could persuade our colleagues could come out of the curriculum. The answer to this probably is very institution specific. In our case, what we really settled on was the fact that our biology students took a lot of chemistry, or at least I thought it was a lot of chemistry. They had to take 7 semesters of chemistry on the way to a biology degree. And pretty much the argument that persuaded my colleagues is that the 7th semester of chemistry cannot possibly be more important than the 1st semester of bioinformatics for an aspiring biologist. And our colleagues accepted that. They agreed to take out 1 semester of chemistry and move the essential material into other classes. So that's how we managed to make room. We also had to work on the math background. So we had to talk with our math colleagues and persuade them to change what they were teaching in the first year to our students. So it's very standard in US schools that if you're doing any kind of STEM degree, you basically spend your first year taking calculus. And calculus is unfortunately really not what you need to learn bioinformatics. We needed them learning probability and statistics and a few other concepts from discrete mathematics. We had to persuade our mathematicians to get that into the first year curriculum. And then we could bring in computational biology, teach it at a somewhat higher level, and get it early enough in the overall curriculum that students could use it in research and reinforce it later in their studies. So all of that brought us to a point where we thought we had done something we could be proud of. We had not solved all our problems. We had run into a lot of obstacles, but we thought we had accomplished something in getting all of our biology students taking what we felt was a rigorous class in computational biology. And so we wanted to go out to the community and share what we thought we learned, as well as learn from others how we might better handle some of the challenges we faced or other ones that were coming up. And that's kind of the beginning of the story of how we shift from the local context to the international context, because this really fed into a lot of my work, working with the ISCB and later with other communities like Goblin and so forth, on how to take the kinds of challenges we were dealing with and deal with them in a more global kind of view. So we had set out with what we thought was a relatively simple task. A few of us had gotten together and we said, okay, we put together this curriculum. Are we doing a good job of it? What does the community think? So we set out to ask, what is the community consensus? So we could say, are we following best practices? Are we doing what the community as a whole would recommend doing here? And so we formed what was called the Curriculum Task Force of the ISCB Education Committee. Originally, the Curriculum Task Force was just 3 people, Fran Lewitter, who headed the Education Committee then, Lonnie Welch, and myself. And we had set out to ask about this consensus. And this was done through a series of surveys. So I believe it was Lonnie was doing a survey of employment ads, Fran of core facility directors, to see what employers of various kinds thought people they were hiring needed to know about bioinformatics. And I did a survey of degree programs, trying to find out, just by going across the web and finding every degree in the area I could, what other people teaching in the field thought was training in bioinformatics should look like. And then we said, okay, we'll put all this together and we'll find out what the consensus of the field is. And the quick summary of all of that work was that there is no consensus of the field, or at least at the time, there was no consensus. There was absolutely nothing that every program agreed on. There was only one thing that even half the programs could agree on as a requirement for a bioinformaticist, and that is a little more than 50% agreed that a bioinformatics education has to include statistics. Nothing else reached even a majority. So we realized that what we were trying to do was premature. We could kind of understand some of the space of options that were out there, but we couldn't be prescriptive about best practices. We needed to go out and get more input from the community and actually foster some dialogue to talk about why there's such a disagreement, whether there are things we could agree on, and whether we could eventually come to some notion of best practices. So this led to bringing in quite a few other people to this effort at understanding what the standards of the field are. So this is a first paper that came out on this with some of the expanded curriculum task force here. Most of these people are still quite active in bioinformatics education. I want to particularly call out Kath Brooksbank, who brought a number of really crucial ideas to this work that she and her team have continued to develop. In particular, the idea that we're not going to get consensus at the level of particular classes or particular subjects. We need a notion of core competencies, so kind of a higher level idea of what a person working in bioinformatics of different kinds needs to know. You heard in Nikki Mulder's talk a bit about the core competencies yesterday, so I won't go into much detail on this. And we also need They also brought in the idea of personas, which we've heard quite a bit about here. So personas would be different learning needs, different representations of what people need to know about the area. Original three personas were the bioinformatics user, the bioinformatics scientist, and the bioinformatics engineer. The user was more or less the biology students. I was trying to teach. The engineer would be more like the computational biology students. We also teach, and the scientist, another role kind of in between, doing what we might call an applied bioinformatics person today. And this was just an example. Angela, bioinformatics user. Since we've seen a number of personas, I'm not going to dwell on this, but basically this would be someone like the experimental biology students we were trying to train, who might mostly be working on running wet lab experiments, but needs to know something about computational tools to be able to work on experimental design, data analysis, interpretation of results, and so forth. So all of that gave us a framework where we could then start to reason about what was the range of practice in the field and why did it differ so much, which often came down to different personas we were trying to teach. And that gave us a beginning from which we could then reach out to the field in a much more general way and try to get to something closer to a community consensus. So at this point, we settled into a multi-year process of many of us in this growing community, really trying to get out and meet with many people working in the field through workshops that we ran at ISMB, at other ISCB affiliated meetings, Goblet affiliated meetings, and so forth, to sit down with scientists working in the area to ask people what they thought of the competencies, how they would refine them, what they thought of the personas, what they thought of the overall process, and lead to a much more refined notion of what this competency framework should look like. We brought in the notion of Bloom's taxonomy as a way of recognizing that different personas might need the same competency at different levels of mastery, broaden the set of personas, and gathered a lot of experience on how these were being used. That led in part to the version 2.0 competencies, which were refined and expanded from the earlier ones, as well as a broader collection of personas that different members of our community could bring to us as different groups that needed training in this area and that might have different levels of mastery that they would need to exhibit with respect to different competencies. Those version 2 competencies were, again, not the end of the process. This continued with really the bioinformatics education summits that you heard about again in Nikki's talk, taking over a lot of this task, replacing these workshops. We have been kind of adding on to other meetings, and these bioinformatics education summits have continued this process with the competencies being a major agenda item at each of them, working on, again, trying to refine the competencies, get much better ideas of how to use them, how they've been used and how they can be used more effectively, and provide guidance to the community on that, and improve them in part by bringing in this notion of knowledge, skills, and attitudes, or KSAs. So a finer level of resolution about what it really means to exhibit a competency. So this resulted in the 3.0 competencies, which were, I think, really completed as of the last summit meeting, where we had not just these overall competencies, but the KSAs talking about knowledge and skills you need to exhibit a competency, and attitudes you either exhibit or do not exhibit if you have this competency. And again, I'm not going to dwell on this because it was covered in a prior talk. But that really is where the community stands. This is continuing, but it is allows those of us working in the area to then go back to the local context and think about how we could handle these kinds of problems better, how we could use this sort of framework to revisit questions of how we would design, let's say, a program, how we would fit our training into that, and really show that we are doing something that in some sense meets best practices of the field. So we could take learning objectives like the class I was showing you, we could represent these in terms of the competencies. This is actually the version 2 ones, but basically be able to say how the learning objectives of our class and the competencies map to a common framework, how different competencies map to different objectives to show what we think a student is learning in our class. Put this in the context of an overall curriculum where other competencies are developed in other parts of that curriculum, and really be able to show what needs to be in our class, what might be superfluous, as well as what's missing and needs to be covered elsewhere in the curriculum. So we could identify, for example, competencies that we didn't think could productively fit in our class, but were also lacking in the curriculum and might have to be covered in other places, and then really go to being able to much more rigorously say, with some real evidence behind us, what this curriculum should look like, how we might need to make further refinements, for example, in the professional development part of our curriculum, in that class itself, as well as in other classes like computer programming. So, for example, we ended up developing our own computer programming for biologists, which is different from the standard programming classes, to replace that. And that put us in a much better position, really more than a decade later, to be able to look at, in some ways, the harder problem of how to provide computational biology education to PhD students rather than undergraduate students. I say this is a harder problem because we have a lot less of their time to impart coursework. They are basically taking half-time coursework for about a year in our PhD program before they go to pretty much full-time research. They're generally coming in with most of them having no prior education in computation. Maybe half of them have had statistics education. Most of them have had no programming, no bioinformatics, and really in a very limited amount of time trying to meet a similar need to what we were trying to meet with our undergraduate biologists. But with the framework of competencies behind us, we could feel that we could do a better job of this. It was put together in a class I developed with colleagues called Data Science for Biologists, where we could then start to think more rigorously about what is the persona of a biology PhD student, in our case, somewhere between what we call the discovery biologist or a molecular life science educator. They kind of needed pieces of those. How would that map into competencies? What is missing from their prior training that we felt we could put into this kind of class? And how we could accomplish that within the constraints of the overall PhD program. So once again, we put together some learning objectives I won't dwell on. We put together a class to meet these learning objectives, built around the idea of having a series of modules where we would try to impart basic but translatable bioinformatics concepts. So things that students could learn in one context, but could apply to other areas, including to novel areas that they're encountering in their own research. So I worked with a series of experimental colleagues on each of these modules. And a typical one might be this first module that I worked on with Veronica Hinman, an evolutionary and developmental biologist in my department, where she would bring some of her RNA-seq data into the laboratory, into the class, teach the students about the problem in developmental biology it was supposed to approach. And then I could teach them about some of the tools you would use for that kind of analysis and bring them into computational workshops where they could work on this. We can teach them various bioinformatic and biostatistical tools that they would use over the course of working with various kinds of data and biological topics. So we could, for example, introduce a topic like clustering in the context of analyzing RNA-seq data and see how it applies in developmental biology. And then when we later visit a problem in neuroscience where we're looking at neural electrophysiology data, expect the students to be able to see how that same concept of clustering translates to a new context and really be able to put that into practice through Jupyter Notebook sessions. So working with Jupyter Notebooks is one of many other things I got from interacting with the bioinformatics educator community as a whole. Lots of these sorts of tools and techniques that many of us use come from these kinds of interactions and allow us to put this together along with other sorts of tools that can allow us to address what we can identify as gaps in the training. In this case, using something called the OLI interactive learning system, which allows us to address some weaknesses in statistical training of some students using a kind of self-paced, interactive tutor, so a computational system that they can use to basically learn statistical reasoning. And we could then see that we were able to do a much better job for really a harder problem of the PhD students than we had done with the biology students from all the things we've learned in working with the international community. That puts us in a position to then go back to the international community and talk about some other ways that these kinds of lessons and these kinds of tools can be brought out to a wider community. And one of the things that was mentioned briefly the other day that I wanted to say a little more about is the ISCB course affiliation and degree endorsement process. So one of the things we've learned from working on all of this is that we have these frameworks now for evaluating contributions to bioinformatics education. We're in a much better position than we were when we first set out to learn what the community consensus was, what best practices were. We actually do have some ability now to speak about best practices in education that have come from the work of many people in the community over a number of years. And this, combined with interest from a number of people in the community in getting some stamp of approval on their own programs, their own short courses or degree programs, saying this program has followed best practices, led ISCB to propose to bring these tools to the community through this affiliation and endorsement process, where anyone can apply to have their degree program or their short courses reviewed and evaluated and basically get the stamp of approval from our educator community saying, we agree that this is a good program that's been developed consistent with best practices of the field. And that really depends on this competency framework and this idea that we can take learning objectives and a degree program and through the framework of the competencies evaluate, is this a rigorous degree program to meet those learning objectives without having to be prescriptive, without having to say what your learning objectives should be because they're going to differ for different programs. But whatever objectives you have, we can say you should be able to map them to a competency framework and figure out what competencies that those learning objectives will entail, map them to a degree program, and certify that your degree program does in fact meet the competencies that are needed for those learning objectives and that match whatever profile or persona you're trying to develop. We put together a process for doing this, an application system that is open now. We are looking for volunteers to beta test the systems. We're really trying to get people to put their short courses and degree programs in this so that we can beta test this process. But basically, we have a whole system where you can put together this mapping, put in info on your program, and a review process to put these through, modeled on a journal review process where we can then have experts from our community review a program and hopefully with often a round of feedback, be able to say that we have reached an agreement that this is a rigorous program and you have the ISCB's endorsement for that. So all of that allows us to once again go back to our local context. And I just wanted to close by saying a little bit about what we may think might be one of the emerging directions here. Because while the community is working on all of these ideas for how to better teach our subject, the subject itself is constantly changing. The technologies are changing, the problems we're solving are changing, the biology, at least what we know about it, is changing. So this is a moving target. And one of the things that we've been working on within Carnegie Mellon that I see as a next step or a potential new challenge for a community is automated science, which is really something that's more in industry right now than in the academic world, but we think is a growing wave of the future. And what I mean by automated science is that much more of what it means to be even an experimental biologist is going to be computationally driven. That doesn't mean people will not be working with their hands in the lab, but more and more often, what is done by a technician working in a lab today is going to be done by robots controlled by computers. If you really want a repetitive task done reproducibly many times and done well, you want a robot doing it, not a human being. And so this is something that we've been working on developing educational materials for, because it's really going to have to be our community that teaches this. This is just a picture of an actual robotic lab we have at our institution. This is the main robot that moves along a track, interacting with different stations that perform various experimental tasks. And we've really been trying to put together a program that will teach students how to do this kind of automated science, including both repetitive tasks, so how to program a robot to be able to do very basic tasks, like in this case, milking a cow or assembling a car, or liquid handling in the case of the actual robot here, as well as intelligent tasks, because often you don't just want the computer telling a robot to do these exact steps. You want the computer to be looking at the data coming out of those experiments, analyzing it, and the computer figuring out what are the next experiments to do based on that. So it really requires not just being able to program a robot to do specific tasks, but to program it to be intelligent, to learn from what it's done, and to propose next steps. So really AI and machine learning. We've put together a new degree program, or Master's in Automated Science, and number of classes to support this, where students can learn about the basics of the actual robotic machinery, how you would program that, the machine learning behind data interpretation, and really bringing it together in automated and experimental design. And this is something I would put forward as maybe an emerging direction for our field. And lest anyone think that this is too hard for experimental biologists to learn. This isn't just something we're doing at the master's level. We've actually brought this into our pre-college program, our high school student program, where they're working with the automated science along with more traditional bioinformatics and actual hands-on lab work to a degree. So I will just wrap up here by drawing some conclusions. There's now a large community of educators, all of us here, as well as many others, who can share our experience and learn from one another. Having a common analysis framework, and in this case, the competencies and personas, really has turned out to be crucial to allow us to speak a common language and to be able to share experiences despite the many differences in the personas we're trying to teach. Once we recognize those commonalities, we can find ways to serve many populations. But I really think this is an ongoing process where each of us is working and innovating in our home institutions in different ways, and then bringing that to the community, and then bringing the ideas of the community back to our home institutions. And this is something that all of us need to be involved in. I'll just close with some acknowledgements here. This was the work that I described of many different people, but I want to especially highlight those who worked with me on development of the classes I described on our automated science program, and many of the players in the ISCB curriculum task force, affiliates who worked on different aspects of this program, numerous workshop participants, and of course the many organizations, including Goblet, that have been part of this international effort that I've been privileged to be a part of myself. So let me stop there, and I don't know if we have time for any questions, but thank you for your attention.
One or two questions. So the floor is open for questions. You may post it in the chat. Yeah, go ahead.
I'd like to thank you for the yes, you hear me? All right, I would like to thank you for the presentation. So I was wondering if you have any collaboration with the universities at the northern part of New York City, like our school at Syracuse University, any collaboration?
I don't personally have any collaborations with them. In the northern part of New York City, I know many people in the area, but I don't have any active collaborations that I can think of with anyone there. I'm sorry.
All right. So, I mean, for biology students, what would you offer just to start from scratch for anybody? who doesn't have the computational skills?
Well, and the main thing I would say is learn them. I think this is often a challenge with our own biology students, that many of them don't think they need to know computational skills. They may have gotten into biology because they wanted to be scientists, but didn't want to learn math and computation, and they thought biology is the way you do that. And really trying to tell them, no, biology is absolutely not the non-quantitative science. You need to know this stuff. It is one of the challenges to teaching this. And I think that doesn't need to be said as much as it used to, but some of the students don't learn that until late in their careers. So just imparting that, I think, is important. And then beyond that, once students are convinced this is something they need to know, I think you need a solid foundation to benefit from it. I would say bioinformatics is really important. You want to learn that before you get too far in your bioinformatics practice. But I would start even earlier. Learning computer programming is a really useful thing to do. It's not that hard, and it can seem hard if you've never done it, but there are now many resources available online for self-teaching if you don't have a good instruction, a good option at your institution, or you're not in an institution of higher learning where you can take that. Probability and statistics is really fundamental there. And there are a lot of great resources online for self-teaching if you don't have the opportunity to take a class on it. But that's something I would, I guess some advice I would give to someone getting into the field.
Thank you.
Thank you. I see there are some questions here. Let's see. Do you have any tips or advice on how to run a good practical class in bioinformatics? Well, I would say that some of what we found is that a practical class, it really does help for it to be concrete. So you can't get rid of lecturing of some kind, and you can have flipped classrooms and all these other innovative ways of handling this, but you have to impart some knowledge. But I think it really helps to have the students getting their hands dirty in the computational sense. So having real exercises that connect to things that a student working in a laboratory can understand are tasks they would need to do that will help them in the laboratory. So it really has to be connected to things where the student will appreciate why they're doing this. And that's something that I would put in a class, and that we found successful in our classes, really focusing on practical tools where by the end of the day or the end of the week, the student can really see that they can work on a computer and do something that will be useful in the lab work that is their primary area that they're really trying to learn. Let's see, there's another question here. For external PhD student like us, if we were working on neurophysiological cancer cells on microbiome computing, is there any opportunities for data sharing, particularly in your university? I'd say that that's very problem specific, and almost lab specific in some cases. More and more often, that's really a community effort of data sharing. So rather than the one institution, and many communities now have their own resources where data sharing is common. My research is largely in cancer genomics, so I'm aware of some of the big repositories of cancer data. So you can, for example, use the International Cancer Genome Consortium's data, the Cancer Genome Atlas's data. I don't know as much about neurophysiological or microbiome repositories. I'm sure they are out there. And that would be the main way you can get a hold of large amounts of data, and often the only way to get large enough amounts for some kinds of computational questions. But on a more specific level, there's a lot more effort in the community to make sure that people doing research are publishing their data and publishing it in a fair way so that it's accessible. I think this is something as a community we need to keep hammering on to make sure that data is out there and is freely accessible. And journals are getting better about requiring this. Funding agencies are getting better, but it's still quite heterogeneous. So I know that doesn't exactly answer your question, but I hope that's some useful content on it.
There's one more question. Do you think it's especially Python for MSc students in biochemistry, or just stick to useful tools in biochemistry?
So the question of whether we should introduce a programming language is something we debated. When I first taught that class for undergraduate biologists, I thought teaching them programming was just not practical within the class on top of all the other things we were teaching, and they didn't take programming first. So I had originally taught it entirely using web-based tools, and I think the students could get something out of that, but not as much as they get if you can bring in even basic programming. So later versions of this I taught, we actually ended up bringing Python into that class. The other class I taught in R. I think sometimes you have to be realistic about what is available. If your students are coming into a class like that with no prior training in programming, it may be unrealistic to teach them programming on top of bioinformatics in one course. It really depends on how much instruction time you have. But I think if you have the time to impart that, or better yet, if you can arrange that your students have programming as a prerequisite coming into a class like that, you can just get much farther. And really, what a student can do in terms of being a computational biologist or an experimental biologist, what you can do with even basic programming is so much more powerful than you can do with web tools, that I think you really want to use it if it's at all an option. Once you can get people over that hurdle, that they can see how much more effective their work can be with some simple programming, you're really setting them on a path to be able to do much more and be much more effective in the future. So that would be my answer. If you can do it, I would.
There's one question.
Yes, I don't see any about green IT skill. Perhaps it should be important to include it in the curriculums. So yes, so this is something that this has come up in some of the discussions about the competencies. If this is a competency or part of, let's say, the attitudes of being a responsible bioinformaticist. I think, I forget now if this ended up being part of the KSAs. I think this may actually be part of one of the KSAs, but I don't remember the details off the top of my head. I'd have to refer to it. But if it isn't there, it is something that I think people working on any kind of high performance computing especially need to know something about today to be a responsible member of the community. So I'd agree, perhaps it should be in the curriculum.
Russell. Thank you. One question: how do you explore the lack of in the different, because you of the addressing how the biologists learn bioinformatics, no? But in my experience, because in my group I have the computer statisticians, or sometimes engineers, how do you explore the lack of knowledge that these kind of disciplines have to do good bioinformatics? For example, sometimes a good statistician doesn't know anything about programming. The curriculum, or for example, a computer science, the level of statistics that they know is sometimes not very good. Yeah, they are very good in the level of the mathematics that they know for big data management is not so good. So this kind of, in the different disciplines, what you are lacking.
Yes, so this is something we've run into, especially when you're dealing with very heterogeneous student populations. You often have to customize your training, but there are trade-offs there. So I can give an anecdote. Our master's program, we used to really explicitly take students on two paths. So some of them coming in pretty much trained as biologists, some coming in pretty much trained as computer scientists, and then pretty much the first year would be getting them up to a common standard where they were both at more or less the same level in biology and computing, and then we could bring them to real computational biology work together. The more heterogeneous it is, the more you have to customize. At the PhD level, we're taking students from many different directions, and some students might have one gap and other students a different gap. We really have to have advisors who can customize the education program to get all of the students up to a common level where they can benefit from the core classes. But there's a trade-off there. And the master's program, we now pretty much are taking students with a much more homogeneous prior background, so they all have strong quantitative backgrounds coming in, and that lets us not have to change as much. We can assume they start at a higher level, and so we can get to a higher level in the end. And I think there's no getting around that trade-off. If you have the resources to have multiple different programs for these different backgrounds, you can do a better job and get people to a higher level than if you don't and you have to offer one program and customize it to many different groups. But everyone's resources are finite, so it's, I don't know a better answer than that you make the most of the resources you have. But of course, the community is working as a whole to make those resources available to everyone. And maybe we'll, as a group, be able to get to a higher level in all of that training by plugging everyone into the right training experience for where they're coming from and where we're trying to get them to.
Thank you for the great talk, and thank you for your effort during your whole career for bioinformatics education. So I have a small question of just out of curiosity. You mentioned bioinformatics or computational biology program that people could apply through the ISCB's website. So I was wondering who can apply for that program?
Yes, well, this is the degree endorsement course affiliation program. Is that what you mean?
Yeah, I just saw, maybe I missed the part of the presentation. It was just like you mentioned that you can apply through the ISCB's website. So anybody can apply that. What do you expect from an applicant?
Well, this is I'm not sure which part you're referring to, but if you mean the endorsement process, anyone with a program or a short course can apply to that. We would want it to be something that exists already and has been offered for us to evaluate it. But anyone who has a program, we're really trying to get applications. We'd like people to enter their programs in there and work with us to kind of beta test the process and get some courses and degree programs affiliated or endorsed, and really help us improve the process, but also start getting some of these out there to the community as things we can point to and say, these are rigorous programs. We hold them up as models that others might try to emulate.
Thank you.
Yeah.
With that, we can close the session, the keynote talk session. Please join me for a round of applause for Professor Russel Schwartz for a wonderful talk.